I don't think I suggested we get anything.
Okay, everybody, welcome, thanks for turning out. Allow me to introduce to you, Evan Hall. He is going to talk to us about quantum teleportation, demons and money.
Wonderful. All right. I gotta share the screen and then we'll get started. Great. Cool. Thanks for coming. So a couple of preferences. Some basics before I start. Quantum computing is like the intersection of like three crazy topics, right? So it's like physics, computer science, and math. So I come barely from the math side. So I don't know much computer science or physics. So take that into consideration when we talk about some of that stuff. But let's get started. Okay, so I'm going to start with some motivation. So on the technological side, Moore's law is the observation that every 2 years, the number of transistors in a circuit doubles. So ever since transistors were invented in the 1940s or 50s, it continued to skyrocket. So now in early 2020s, Apple has like 100 million transistors in their chips, and they're so small, it's such a small chip that at this point it's starting to intersect with things at the quantum level, so that companies will literally put a lot of money into making sure that the quantum mechanics don't affect the circuits right now. So as we increase the size, it's better to maybe work with the quantum mechanics than against it. So then here's a quote from Feynman: when we get to the very, very small world, say 7 or so atoms, the atoms behave nothing like on the large scale. They satisfy the laws of quantum mechanics. Great, so that's the tech thing there. So what is a quantum computer? One big misconception is oh, it's just a super fast computer, but that's actually just not the case. So a quantum computer uses the powers of quantum mechanics, such as superposition, entanglement, and decoherence, to do massive parallel computing. So this means that there's some tasks that quantum computers can do much, much better than classical ones, but not every single task. So what are some of the tasks then that quantum computers can do much better? We'll look at that right here. So for classical computers, as the input size of our the matrix problem line grows, the problem moves and becomes much harder. So one such problem is given an n-bit integer, find the prime factorization, right? So if you just plug in chug this, you have to check all the way to square root of n, right, for the number. So that takes a long time. But the fastest algorithm with a classical computer takes complexity of 2 to the cube root of n. So I don't know if you can kind of see if there's a squiggle in front of the O for the complexity, which means that it can also have log n's and stuff in there too. But overall, it kind of behaves like 2 to the cube root of n to find the prime factorization of the number classically. And then with a quantum computer, there is proven algorithms to find it in O of n cubed, which is insane. That is Gaussian elimination speed. That's crazy, right? So that was proven in 1995 by Peter Shor, one of the goats. And then prime factorization is pretty huge, right? It's what we use for our encryption now with RSA. So once quantum computers scale up and can actually do this, we're screwed. So that's relevant to cryptography. Another problem that quantum computers can also do much faster is the discrete log problem. So if you're given 3 n-bit numbers, a, b, and n, find the promised integer s such that a to the s is congruent to b mod n. I say promise just because for existence. And then so classically, we can do this in super polynomial time n. And what that means is that as n grows bigger, there is no polynomial that can bound the size of this. So, which is similar to the first one. Here we're exponential, because that'd be example signs also super polynomial. But there's also another algorithm, also by Peter Shor, which was actually found a week later. Actually, I think he found this one first. But he can now do this in polynomial n time, which is linear time, right? So that's pretty insane. And then, so the first one was for RSA, and the second one is for discrete log. And so this kind of problem, you're dealing with primes and modules and stuff, shows up in number theory, algebraic geometry, and there's also cryptography that's based on algebraic geometry, algebraic geometric codes. So that's also done because of this problem now being able to be solved in polynomial time. I forgot to set time, so I don't share. Anyways, and then the third problem that can be sped up is not like the other two, but if I have it's like a searching algorithm. So if I have, so it's searching like a database where one thing is like highlighted, you can think. So here we can represent that as a function. So if I have n things, and I have a function where one of the things will get sent to 1 and everything else will get sent to 0. They're asking you to find the marked thing. So it seems like pretty complicated, or not, there's no good way to do that, right? You just have to go and start plugging things into the functions, see if you get one or not. So I'll write down one little thing. So the algorithm that I'm going to talk about is like be confident. So for a 50% confidence that you can find it, classically, we can do that in O of n time, which makes sense, right? You have to just O of n. If you want to check 50% sure, you would check half of it. That's n over 2, which is O of n time. But you guys want to guess what the quantum computer can do it in? That would be pretty insane. It's actually square root of n time, which take a second to think about that. I can find some randomly marked vector out of like a big, like, I got a hot, like, needle in a haystack. I can find it in square root of n time. Insane. So then I mentioned that these problems are useful outside of quantum modeling because the first two are related to cryptography, and the third one, probably some computer science application that we don't have. Great. So those are some algorithms that can get sped up with quantum computers. So now we're going to kind of get into the meat and potatoes. So we're going to talk about a lot of mathematics now to build up to one of the crypto protocols I want to talk about. But we're going to do a lot of starting from the ground up now. So classical computers use bits, which can either be in one of two states, in the 0 state or the 1 state. And then quantum computers are built with qubits, which adhere to the superposition principle, which means that they can be in 2 positions at the same time. So you can think about that as the 0 state and the 1 state at the same time. You have alpha and beta as coefficients. And we call these coefficients probability amplitudes. They're complex numbers. And we have this requirement that the mod square for each component sum to 1. Okay, that's fine. Yeah, so then one nice analog you always hear about is that the classical bits are like the light switch where it's on and off, and then the qubits are like the dimmer switch because it can be in a superposition, except for it can also rotate and twist and do other things. So, but it's still a good analogy. So if you try to observe the state the qubit is in, you will see it will be in the 0 state with probability mod alpha squared and 1 with the probability of 1 beta squared. So squaring the amplitude length yields the probability. So that's put that in bold because we're going to see that a lot. So here's an example of that. So if I have this qubit, which I'll call psi, and then the 2 probability amplitudes are 1 over root 2 e to the 3 pi over 2, and if I combine it, we can see that because I'm in the nice polar form, then if I square both of their amplitudes, they both get 1/2, which means that they will have equal probability of being observed, right? And then by that logic, I could have picked like anything for the theta up there, and I can still get a whole lot of qubits that also have half probability of observing what you want. So now into the math perspective. So qubits are unit vectors in C2, which are represented as column vectors, which we'll call kets. So it's like physics notation. And then instead of writing the 0 state and the 1 state, we're going to give them 2-dimensional vectors in C2. The vector 1, 0 and 0, 1. We're going to call it the computational basis. And it's called the computational basis because we have 0s and 1s. That's easy to work with the computer, right? But I could have picked a bunch of different bases, right? I just need 2 vectors in C2 that are going to be orthogonal. So there's no middle term probability. It's going to be nice. But 0, 1, and 1, 0 is perfect for us for now. So remember that the probability amplitudes alpha and beta are from complex numbers. It's a unit vector in C2. So there's a couple different ways to write that. Great. And then we said the column vectors, which are the quantum states, are called kets. And then we have these things called bras, which are the conjugate transpose, which is like the complex conjugate. And I can make it into row vectors, and this will make it so I can have an inner product. So it's kind of the analog of being able to multiply 2 vectors, which I'll have an example of that in a second. So this is seen as a linear functional, which will map quantum states to the complex number C with the standard inner product. And I have some comments and examples, and let me find my notes. What I wanted to say. Of course, I didn't bring it. I have something to say about it. So, so for example, so let's say that it's outside, and it's, let's just say it's equal to the computational like zero vector, so 1, 0. So if I use my broadcat notation and I want to find what psi is, so the complex conjugate of 1, 0 is a row vector, but the complex conjugate of real numbers are still real numbers, right? So like 1, 0 and 1, 0, is that right? Yep, will give me just the vector 1. And I'm not going to talk about what that means yet. We'll talk about what this actually does and what the representative means. But here, if you take the quantum state and use the same linear function, you'll get itself. So, yep, that is the broadcat notation, and then together they form an Hilbert space, which is just like a fancy way to say it's a vector space over the complex vector space. And then the addition to make it a Hilbert space is we need completeness, which is a way to say that we need the Cauchy sequences when we have convergence. Any Cauchy sequence of states will stay in the space. Which when I first learned that, I was like, okay, why would we need completeness? And then it turns out in practice that quantum states are like modeled with waves and particles means calculus. And when you actually apply it, that means we have to get the engineers and the physicists involved. And when you get engineers, physicists, and math together, you're going to get a whole lot of approximating Taylor series stuff. So when we do integrals and stuff, we want to make sure everything converges. So that's why we need an extra step for completeness to make it into a Hilbert space. So that's what we got there. So now back to the qubits. Let's say I have this qubit T, which has these probability amplitudes in the 0 state and the 1 state. And then I multiply P times like P I theta 3. So I could think about that as a separate quantum state. And then notice that they have the exact same probability distributions. So if I was to look at where the first one, how often the first one is in the 0 state, it would be R1 squared. The second one would be also R1 squared. So what we're going to see is that if I multiply any quantum state, like easily I theta for any theta, it'll keep the exact same probability distribution. And we call that a global phase. So they're indistinguishable. And so what that means is that we can actually represent a qubit with just 3 real numbers, right? So if I just look at the R1 from the first amplitude, R2, and I take the difference of theta 2 and theta 1, which we'll call the relative phase, seems reasonable, then I just represent my qubit as just 3 real numbers. And that's great, right? Because who wants to, it's kind of hard to visualize 4-dimensional space, but it's really easy for us humans to look at 3-dimensional space. So we can actually get some visual representation of what this looks like right now. So speaking of threes, throw back to calculus 3, where we had spherical coordinates, right? So looking at that last bottom line with Z, X, and Y, if I apply spherical coordinates here, and with R being 1, we can see, I can use Euler's formula and get the cosine of theta in the 0 state plus EBI B of times sine theta in the 1 state can represent our state B. Sorry, stop. So one additional step we need is because in polar coordinates we need that angle from the z-axis to be all the way up to pi, or no more than pi. We have to restrict the angle. So we get this nice way to represent qubits now, where if I find theta and B, I'm pretty sure I'm supposed to have an R in there somewhere, or whatever, something's supposed to happen. I might have messed something up. I can now represent my qubits. We're good. And so one thing to note is I can represent every qubit now on this block sphere, and they're not unique. So at this green vector, which is this quantum state right here, it's actually not just one qubit, right? Because we talked about the global phase last time. So everything with the exact same global phase will be represented at the same point on the block sphere. So there are equivalence classes under global phase. So that's a nice visual representation. So we talked about what qubits were, the space, mathematically and then how to visualize them. So the next question is, what can we do with it? So there's two things you can do with a qubit. You can do unitary evolution, and you can also measure it. So let's talk about unitary evolution first. So unitary is for unitary matrices. So unitary matrices are super nice, right? They have some nice properties. Their inverse is their conjugate transpose. They have determinant one. They have orthogonal eigenspaces, and most importantly, they preserve the two norm, which means I have the exact same probability distribution if I was to apply U to my state. Oh, and not to mention, they're also invertible. So if I apply U, I can also go back to my quantum state that I had originally. Okay, but yeah, the kicker is that I preserved the two norm, which is great. So some common unitary matrices, which we'll call gates that we can apply to single qubits, are these four. We have the poly X gate, Y, Z, and then also this Hadamard gate. So I want to talk about what these kind of do to a qubit. So I look at poly X, which looks great with the identity matrix. And then let's say I have just like a zero state, like quantum state in the zero state, so 1, 0. This clearly just maps into 0, 1. So the X state just flips the probability amplitude to the qubit. And then a couple more. So then a couple other important ones is Z gate. So 1, 0, 0, negative 1. And then if I just have some qubit alpha beta, then what happens? I get sent to alpha and negative beta, which means I actually flip the phase of the second, which means I actually flip the phase of the qubit. So I rotated it by like pi degrees or degrees. Yeah, so that's, and then, so yeah, so the poly X gate flips the probability distributions. The poly Z gate flips the phase. The poly Y gate, actually, you can kind of see it's reminiscent of the Z and the X. So it actually flips the bits, flips the phase, and it also multiplies it by I. But multiplying by I is the same thing as applying e to the I3 pi over 2. So that's kind of like a global phase change. So actually the Y gate is actually the X gate times the Z gate times I. So written out, that would be that the poly Y gate is just I, that's right, e to the I3 pi over 2 times X times Z. So that represents phase flip, bit flip, and rotations going on there. And lastly, the Hadamard matrix, which is great because here's one of our quantum principles. So if I have 1 over root 2, 1, 1, 1, negative 1, so qubit like well in the zero state, what this will do is I get sent to 1 over root 2, 1, 1. So if I measure this now, it means that I'm going to be in the superposition. It has changed my zero state vector to be in like half superposition in the 1 state and also the 0 state. So the Hadamard gate is really useful for making things go into the superposition. Okay, and then these four are like used all over the place. And I have a 4-dimensional space between two matrices. I need 4 vectors. And the identity along 3 polygates actually gives me a really, really nice basis for the space of all 2x2 complex matrices. Great. So that was one thing I can do. I can act on a qubit with unitary evolution. The second thing I can do is like I can actually measure it. So kind of like looking at the quantum state, is it in the 0 state? Is it in the 1 state? So I can actually measure it. So the possible results of measuring physical quantities correspond to eigenvalues of self-adjoint operators, which just means the eigenvalues of those matrices we were just looking at are what we get when I measure. So I have some examples for you. So if we're looking at the Z gate, you can maybe tell by inspection what the eigenvalues are. So Z gate, which is 1, 0, 0, 1, has eigenvectors of 1, 0 with eigenvalue 1, and then it has the eigenvector 0, negative 1 with eigenvalue. Wait, I didn't try. Oh, that's right. Eigenvector 0, 0, 1 with eigenvalue negative. Great. So after I measure in this Z gate, what I'm going to end up getting is the one 1 or -1. So let me show you what that actually means. So let's say I have this qubit right here, which was able to use 0.6 and 0.8. I took out the whatever just to make it less complicated. So to measure something in this computational basis with the z state, what it looks like is I can take either one of these eigenvectors and throw that into a bra, and then I just operate on it with psi, and it'll give me probability. So let's see what that looks like. So if I just take one of these eigenvectors, I'll pick the first one. So if I do 1, 0 times my vector 0.6 and 0.1, and then it makes sense here. Notice that these are the same eigenvectors are also like correspond to the same basis here. So if I do this product, then I disconnect 0.6 and throw out that slide like 10 slides or a couple slides ago, where this is kind of like a projection, and to get probability I have to square stuff. So it turns out the probability that I get the 1 state, I'll show you that I get the 0 state is 0.6 squared, which is 36%. Write the exact rest of this out. So so I chose one of the eigenvectors here, the 0 state, and then when I operate on it, it told me the probability of getting the 0 state. So I could have picked either one of the eigenvectors, and it would have given me like the same information, just reversed, right? So I would have known that I have 64% to get my 1 state if I picked the other eigenvector, no matter what. Yep. Okay. Oh, great. And then one more comment to kind of put things together. The Z gate and also these eigenvectors being the computational basis, you can actually see that on the block sphere, how the Z axis corresponds to the 0 state and the 1 state. And then I can also have like different bases that maybe go on the Y state, the X state, we'll talk about later. Great. So those are the 2 things we can do with qubits. We can measure them, or we can evolve and apply operations to them. Did I go too far? Yes, I did. Gosh. Great. Okay. I'm so sorry, I can't see this. How do I? Oh, no, okay, so the dot says mutually unbiased bases, I think. So 2 bases are called mutually unbiased if the eigenstates of one are equally spread out with respect to the other base, which I couldn't think of a better way to word that, but I have a good example that shows that. So to show you that the X and the Z gates are mutually unbiased right now. So the eigenvectors for the Z gates are right here, and I just gave you what the eigenvectors for the X state are. We call it the plus state and the minus state. So let's say I have a vector. Let's say I have a quantum state. Let's say I have a state, quantum state, which is the 0 state, which is 1, 0. And let's say I apply the plus to it. Then what happens after I do this measurement is I get 1/√2, which means I get probability of 1/2 of seeing the plus state. And no matter what combination I get, I always get 1/2, which means that if I have a vector in that was prepared in my Z state, if I measure it in the wrong basis, like the X basis, I don't get any information. It just spits out, oh, maybe it's in one side, maybe it's in the other. I just have 50-50 chance. So I have no information that I gain. So that's why these things are mutually unbiased. So I could have picked different bases, and maybe the probabilities would have been different, and maybe some information can be taken out of that. But that's why the X gate and the Z gate are really good, because they're like kind of like orthogonal. Great. So next we're going to talk about tensor products. So before we've just been talking about 1 qubit and what you can do with it, but you can't really build a quantum computer with 1 qubit. So we need more than 1 qubit. So a state of multiple qubits can be made using tensor products of individual states. So a possible basis for a 2 qubit system is if I have 2 qubits, I do this tensor product, which if you haven't seen that before, there's a nice easy way to see what's going on there. Let's do this. So if I have like vector AD and I want to tensor by CD, I'm kind of doing a vector that's like the size of these 2 things summed together. And what I do is I look at the coefficient of this thing and I apply it to CD. That becomes my top thing. So I get like AC and AB. And then then I get B times CD, then I put it right underneath, so I get BC and then BD, so I get this like vector out. So you can kind of see that here. So I do 1 times the 1, 0 vector, so I get that again, and then I do 0 times the 1, 0 vector to get 0, 0. So I make this 4-dimensional vector, which represents a two qubit system, right? I have 2 qubits now, so here, this is the state where both of them are in the 0 state. So a possible qubit state for like 2 qubits could look like this. There's 4 possible states 2 qubits can be in. They either both be 0, both be in the 1 state, when you measure both be or in the 1, 0 state or the 0, 1 state. So this is like a probability distribution that would work. Again, so yeah, we can have multiple qubit states, and then yeah, obviously we want lots of qubits, so we can do things. And the tensor product is what lets us make larger states. So, all right, let's get into some of the weirdness now. So this is what kind of gives all the quantum computers their power. So entanglement, classically, physical objects can be broken down into pieces which can be described and measured individually. So calculus, right? We can find the position, the acceleration, the velocity at a time t. We can do that. We can look at different components of a physical thing. But quantum systems can have states that cannot be described by individual components. And we call these two things, we call qubits that cannot be separated into individual parts entangled. So the 2 qubit state that can be written as a tensor product of individual qubit states is like this. So here I like label the things for you guys. So there's like the first qubit 0, 1, and the second qubit 0, 1. So if I can separate my quantum state into like only things from the first qubit and only things from the second qubit, make that into a tensor product, then the thing would not be entangled. But here's a quantum state, 1/2 of being in the 0, 0 state and the 1, 1 state. This is actually an entangled state because I can't write it as a tensor product of this. And to actually go through and check if it's entangled or not, you write this as the column vectors of 4 things, make a nice linear system, and then you would solve it and see if you could make it into something above. But that's left as an exercise for you guys. But this is an example of an entangled state. And so it cannot be separated into a tensor product. Here we go. And it's also important to note that, like, if I do something, if I have 2 qubits that are entangled, you guys have probably heard, like, if you do something to one, it's going to get affected, the other one's also get affected. And what's crazy is that no matter the distance, if I apply some operation like some of those gates, like the X gate and the Z gate to the first thing, it'll affect my second qubit no matter where it is, which we'll talk about that in a bit. So quantum teleportation is the next thing to talk about right after entanglement. So quantum teleportation is the protocol for transferring the state of one qubit to another qubit without physically transporting the qubit itself. So this can be done if you have 3 qubits and 2 classical bits. And it uses entanglement, so that's what I'm talking about around here. All right, I'm about to give you guys like the most hand-wavy sketchable proof of all time. It's not a proof, but the most hand-wavy kind of idea of what's going on because I'm not a physicist. But here's what's kind of it's fluffy real. So let's say that there's 3 qubits. So let's say that we have Alice and we have Bob. And then here they share an entangled qubit. So there's 2 qubits and they've been entangled beforehand, and then Alice has one of the qubits and Bob has the other. And let's say that Alice also has another qubit. Okay. So together she can make this into like a system without like entangling everything. You can just kind of put qubits together into a system. So we have a 3 qubit system. And you can see the very, very top thing here is like, here's my lone qubit, something in the 0 state plus something in the 1 state. And then here's my entangled state from before, right? So that's what our system could look like. And then if you actually like combine these things and use that tensor product we talked about, you can write that as this right here. All right, this is where the hand waving begins. But we didn't talk about matrices and operations to do out like multiple qubits. But basically what Alice is going to do, because these things are entangled, whatever she does over here is going to affect whatever happens over here. So she's going to do some operations on her 2 qubits, which I kind of wrote down here. Don't ask me about which operations they are. But then she's going to end up with like some state like this. And then, so after she does a bunch of operations, she's going to kind of jumble some things up. She's going to measure what her 2 qubits are. And either she's going to get 1, 1, 1, 0, 0, 1, or 0, 0. And then it turns out that after she measured what her 2 qubits are, she's gonna go like, communicate through a classical channel with the internet and tell Bob, okay, these are my 2 measurements. And then with the information that Bob gets of what these 2 qubits measured to be, he can apply some operations to his qubit, and it'll be the exact same state as whatever this thing was. And I'm sorry I can't give you a deeper explanation of what that is. That's kind of how I understood it, and that's how I'm moving on. So that's a celebration there. Great. So next we have 2 fundamental, I'm not sure what I wrote there. Anyways, 2 fundamental things in quantum mechanics. One is the Heisenberg uncertainty principle, which says that we can't measure certain pairs of properties at the same time, such as the position of momentum, which we can do classically, right? If you have some memory in your classical computer, you check it, it's still going to be there after you right? But after you observe a qubit, it actually gets collapsed into one of the states. So if I have my qubit like alpha beta, I measure it in like the z basis or something, like I'm going to get 1 or 0. And I'm going to get either 1 or -1 for which eigenvalue, right? But it collapses the state, so I no longer have this like nice property of like being in a superposition anymore. So the Heisenberg uncertainty principle says that I can't have like multiple ways to describe the qubit at a time without describing them. The second thing is the no cloning theorem, which states that it's actually impossible. In fact, any qubit in any state like alpha beta, there's no way to clone it. Which a good way to there's some proofs online, but one kind of proof that's kind of handy that I kind of like is that if I have some qubit alpha beta, and I have like some like state that I can like change, there's no 2x2 unitary matrix that I can do to this thing to get alpha beta again, or sorry, to make 2 copies of alpha beta. So that's what the no cloning theorem says. And then both of these things are super important in cryptography because it gives us a little bit of security to play around with. So we'll talk about that too. Okay, great. So we did all the build up to talking about the protocol now. So motivated by the no cloning theorem, where we can't copy quantum state, it seems like a really good idea to use this for money, because one of the problems with money is that you can counterfeit it or make counterfeit. So we can suppose that what if there was a way to make money where the qubits were trapped, had a bunch of qubits that were trapped in like 1 of 4 ways. So I mentioned like in practice, the engineers and stuff, they like trap photons and stuff. But here we can think about like qubits prepared in like different ways. We can think about that as the 0 state, the 1 state, the plus state, the minus state from before. Like so the eigenstates of the x basis and the z basis. So either like maybe the 4 states could be 0, 1, 1, 0. What was my plus state? One over root 2, 1, 1, and 1 over root 2, 1, 1. So let's say that I could prepare qubits in one of these 4 states and like make a sequence of them and some money. To replicate a whole bunch of these states, one must determine the base for each of these photons. And if you don't get one of them right, then it's going to collapse it, and like a whole bunch of things go wrong. So if you have a 50-50 chance of like copying each qubit and you get a whole bunch of things, it's like nearly impossible though to copy an entire build, which is where the money thing came from. And so motivated by having this idea of like measuring or making states that are going to be hard to copy, we had this crypto protocol that kind of is made from this idea. So this thing is called quantum key distribution. So the motivation is that if you need to send information to someone over a noisy channel like the internet, you want to be able to share a secret, and that's kind of hard to do it because people can be spying on you over the internet. So classically, if I want to send information securely or send the key securely, I would use some kind of problem that hardware computers now factoring or discrete log, which you see is a problem in the near future. So a key distribution that's quantum actually has security only rely on the fundamentals of quantum mechanics, which is actually insane if you think about it. That means that there's no way to to like spy on someone and get their key unless you like let's tell you about quantum mechanics is just like one, which, it's whatever, right? It's like basically unconditionally secure if we can add something that relies on quantum mechanics, which is what this is. So we're going to see that if a third party tries to each drop a key, they need to collect it, but then if they collect it, they have to measure it, which messes with the state along the way. So through a quantum channel and a classical channel, we're going to talk about how Alice and Bob can share a message secretly, 100%. Great. All right. So this is the vertical we've been building up to. So actually, we'll leave the axis there. So here's the z eigenstate basis. So remember that the z eigenvectors were the 0 state and the 1 state, and then the x eigenvectors were plus state or minus state. So I'm going to give them these names of like psi 0, 0, psi 1, like labeled as such. And so here's what Alice is going to do. First, she's going to pick a random message vector and a random basis vector to prepare her qubits in. So I have the starting some example right here. And I guess I was going to do it on the board. So I will do that actually. So let's say that she picks 2 random vectors. Well, I pick them, and she's going to have a message vector. So Alice has a message, and it's random. So we're going to say it's 10110, right? And she's going to try to transmit this message to the bottom. And then she's going to prepare with the basis chosen by this randomly chosen binary vector here. So 11100 is the basis. She prepares basis for prep. And then, so how she prepares them is that for her message basis, that becomes the first index of our psi thing here. And then the second index is what completes this to tell us which of the 4 states she makes each vector in. So for example, if she has 1 and 1 here, then she's going to go find psi 1, 1, which is the minus state, and then psi 0, 1, the second qubit, plus state, right? It's all about psi 1, 1 again, which is the minus state, right? If I make a mistake, let me know. And then psi 1, 0 is the computational 1 state, and psi 0, 0, which is also the 0 state. Wait, they're the same one. I know we're good. Great. So she prepared 5 qubits in these 4 states. We didn't make this actually quantum state, or it's the quantum state like 0, 0, 1, right? And she can send these through that classical channel here, right? So she sends them to Bob, these 5 qubits over the quantum channel. So then now what Bob's going to do is he's going to pick a random basis to measure each one of these qubits in to get an output vector. So, thank God, the one paper I didn't bring was my example. Great. So let's say that Bob is going to pick this basis to measure his qubits in. So he's going to measure these 5 qubits in. Oh, sorry, but Bob doesn't see these 5, right? He sees these things. What does he see? Bob just sees 5 qubits actually. So Bob just sees 5 qubits. He doesn't know what state they're in, but he's just going to guess and he's going to start measuring. So the 5 bases he's going to use, he's going to measure in the z basis, x, z, and then z. So, okay, and then so with the z basis, right? So we pick eigenvectors to measure, and then we output the eigenvalue. So let's do a couple examples of what that happens here. So here's the qubit. Bob doesn't know it's this qubit, but if he picks one of the eigenvectors from the computational basis, like for example, like 1, 0 to measure minus state, which is 1, 1 or 1, 1. What's going to happen? So he's going to get an eigenvector. He's going to get an eigenvalue out. So let's see. So I'm going to pull this out. So I get 1/√2 times 1, which corresponds to just 1/2. Sorry, 1/√2. But which means he gets probability 1/2 got to square it of getting 1 or 0. So what happened right here? He picked the z basis, right? And this is the wrong basis. This is the x basis, right? Because the x basis was the xz basis. So because he picks the z basis, we talked about how they're like mutually unbiased or whatever. You can see how he has a 50-50 chance of getting it right or wrong, right? So I made it so that the first 2 qubits, he picked them in the wrong ways on purpose, right? So that means that for these qubits, the first 2, he'll get a 50-50 chance of getting them right or not. So let's just say that he measured like 1, 1. These aren't going to matter, you'll see later. But now let's do an example where he actually gets it right. Let's see here. So for example, like 1 in z. So if I was to pick any eigenvector from z, so let's pick the other one now. So if I pick the 1 state, which is 0, 1, as a capital wrong, and then I do that to the computational 1 vector, which is 0, 1, then the output is 1, which means with 100% probability, I am the 1 vector. So he actually gets this thing correct. So if he happened to guess the 1 state and he got the 1 state with 100% probability. So what happens if like he tries to guess to the 1 state now for this last thing, which is the 0 state. So 0, 1, and now he guesses he's trying to guess the 0 state, 1, 0, 1. So now he gets 0 as his probability, or whatever. 0 is his probability amplitude. Once he squares it, that's also still 0, which means he has a 0% chance of getting this, which means he knows he has a 100% chance of getting 1. So he asks him what the vector is, or he knows that this is supposed to be 0. So, right, so he could have picked either eigenvector here, and either he would have gotten 1 or 0. So it either has a 100% chance of succeeding or 0% chance of failing, if that makes sense, right? So if he picks the right basis, he'll get the exact same thing out. If he picks the wrong basis, it's a good chance because it's usually I forgot what the term is, mutually unbiased or something. So leftover, okay, so what the last part of the protocol is now that over the public channel, Alice and Bob will now share what basis they use. So Alice used like the XX, CZ basis, and then Bob used the CZ, XZ basis, whatever. And then so what they're going to do is they're going to take all the things that they did not agree on, and then they're going to cut that out. And it's like the values that the bases that they do agree on, or whatever happened. I think it's supposed to also do something. They would keep those. And what's crazy here is that they announced their bases things over online. So this vector, but they did not, like, Alice did not give away her message vector, and then Bob did not give away what his answer was. So actually, once they cut things out, there's 100% security, and there's no way that an adversary like you could spy on them to figure out what their thing was. So you have 100% chance, or sorry, you have perfect secrecy to send a message. Which is what I'm trying to say. So that's what this quantum computer solution does. So this sounds great. So what's the problem? Why aren't we using this right now? And the problem is, unfortunately, quantum computers are prone to errors. There's things called decoherence, where like the qubits interact with the things around it, and channel noise, like there's like noise, when you transmit information over a noisy channel. And like if we actually were to make a quantum computer, it would use like physical things, which could have problems. So errors are always going to be present. So algorithms like shortest factoring algorithm to break security now, we need like 4,000 qubit computer to break RSA. But you need accuracy to work, and we don't have accuracy. So what we need is error correction, which is kind of like where my research is kind of like heading towards. So error correcting methods for quantum computers. So if we add extra qubits into our space, we can use those extra ones as like redundancy to be able to correct errors, which I'm not going to really get into most of the time. But oh yeah, so if we add an error correction, so a quantum computer that can have error correction can actually implement Shor's algorithm, but you need a lot more qubits now. I think I was like reading online that you need hundreds of thousands of qubits, or like maybe even like 1 million qubits to actually use a quantum computer that can do Shor because of errors. So I'm almost out of time. Let me just skip through some of these slides. So Yeah, well, the thing about the daemon was that it's kind of strange that quantum error correction is even possible because we have those weird laws of like no cloning in the Heisenberg, but it actually is. And won't get into that, but it's similar to this physics style experiment where there's like a demon, of course, who can control this like gas chamber of like hot and cold particles, and you can open a gate in the middle really fast to like move all the hot particles to one side, all the cold particles to the other side. It's very analogous to quantum error correction, where during transmission, we need to be able to like fix errors really, really fast for this to actually happen. And it's kind of like the whole headache of like what the heck's even going on. So we'll leave that to the physicist. I'll just assume it works. So we're basically almost at like 2 slides. So the roadmap with quantum computers. So right now, the more qubits you have, like this is like a crazy complex dimensional space, right? So if I have like this many qubits, like it's gonna be near impossible to like do that on a quantum to simulate that on a classical computer. So these are the sizes of qubits I can simulate. This is kind of where we're at right now. And then with this one thing that's circled here is called quantum supremacy. So this is like the largest, the first quantum computer, the smallest number of bits or qubits that we got that can actually do an algorithm faster than a classical computer. So which is kind of cool, right? I think we only need like 50 qubits or 100 qubits, I forgot. But it's saying here that we actually need like on the order of like 4, 5, or 6 to actually have useful error correction, which is not for a while. Great, and then my last slide is just talking about what the current scale of quantum computers are, which we do have right now. So in 2019, we have quantum computers with 27 qubits. 2023 last year, I think still about now, we have quantum computers like around 1,000 qubits. And then these IBM websites, they have like crazy projections. Like we're going to have 1 million qubits by 2030, but it seems to be like a lot of companies are putting a whole bunch of money into this right now. So it's a pretty hot topic. Yeah, great. Does have any comments, questions? Yeah. Shall we? Yeah, sure.
I was gonna ask you, it's kind of interesting, so you work on quantum error correction?
I work on, okay, so I'm classically, last couple of years, I've been studying regular error corrections, like how regular computers have errors and whatever, over your channels and how to correct that. And then I saw it was applied to this, so then I'm like, that's pretty cool. So now I've just been reading a bunch of physics and trying to bridge the gap.
Yeah, the reason I'm asking that, yeah, that's really cool, but I'm curious about, because I remember, I can't remember what's the relation between how many extra bits you need to have a pure, like, 100% guaranteed, no error over this number of bits for classical. I can't remember the number, let's say my life right now.
Yeah.
Versus quantum, how many qubits you need to correct this number, let's say n.
For sure, yeah, so,
What's the formula? Because it seems like, it appears based on what you said, it appears that you need a lot more quantum bits to correct.
right, so it depends on how many errors you want to correct. So let's say that if I wanted to, I think I was just looking at a code this morning where, hold on, what's the counter? I think that if you want to be able to correct like one error, like one payslip or one x error, or like one payslip error or one payslip error, like you need 9 qubits instead of 1, or it was 3 instead of 9. So like there's some small examples where it's like
A lot of qubits to correct them.
yeah, but the 3 to 9 or the 1 to 9, I forgot what it was, like it can correct one flip or one. So it can correct one hex error, which is like where you flip it, right? Or maybe went to VA, and you can also flip, you can also correct the Z, which is like where you flip the phase. So it can correct one of each of those, which is actually pretty great. So that either one of the 3 qubits. So it was 3 to 9, I think.
Oh, that's interesting. So number of qubits is dependent based on the operation, based on the gate. So errors that can be experienced during the
Yeah,
gate.
and so the common types of errors that you can have are actually those Pauli gates, well, not the identity, but X dividing the Z, which is kind of interesting, right? There's like a whole bunch of unitary matrices out there, but it kind of actually also makes sense. The types of errors would be that you flip the bits or the phase gets flipped, or you do both, right? So these are the common types of errors that you can see like in practice.
Okay. And so does it scale a lot worse than compared to classical error code theory, or like a basic?
I mean, 2, yes, just because you can have different types of errors. Classically, like we love binary things in classical computing theory. Like the only kind of error you have is like the bit gets flipped, the 1 goes to a 0. But in quantum, like you can have a whole bunch of different kind of errors. So because of that, then yeah, you would probably need more things to correct stuff. Okay, thanks. Cool. Any more comments or questions?
Yeah, I have a question. This just reminded me of one other little question I had bringing up the gates.
Yeah.
The poly Y gate, when you defined it, it had this multiple by, I think, like e to the 3 pi over 2, which I think was the global phase.
Right.
If things are unique up to multiplication by that, then what is the purpose of that representation instead of just having integers?
Yeah, good question. Where did I already?
Seven?
Yeah, so one of the, so I didn't call them superpowers, but some of the quantum superpowers that we talked about, like decoherence and entanglement and other stuff. One of the things I did not touch on, which is this thing called interference, which is like the only reason that phases is kind of useful is for this thing called interference, which is like a really physicsy like application of like how the qubits affect in waves. And I'm looking for a good road of how I'm trying to explain this or give you this information. It's like a channel right now. Trying to be but yeah, so yeah, we don't care about the phase at all, except for this thing called interference, which is, I just have to say something, it's like sometimes you can have like the probability of, never mind, let's talk about this after, and I can tell you some application for this.
I do want to say one thing real quick. I actually wanted to bring this up, but
yeah.
Don't unitary matrices, I hate you this guy, but you don't unitary matrices have determinant e to the I, like e to the I some phase.
They actually have determinant one for sure, because if they preserve the two norm, then nothing gets stretched or anything. I think you can check all these determinant stuff. Determinant one.
The reason why that's a little strange. Oh, you say preserve the two norm, I actually don't know what that is, sorry.
Oh, so it preserves the length of vectors. So like a length one vector gets into a length one vector. If you like think about not even qubits anymore, or like one dimensional or length one vectors, if I just like add some like random complex vector, like I don't know, or whatever, let's just move it against that 3 and 5. And whatever this length is, it'll get sent to a vector of the same length. So unitary matrices too. So they preserve the two norm. It's like in here, and after this length will also get sent to a vector of this length.
So you're saying that if the determinant was actually, if it actually had a modulus or it's like an absolute value of 1, it will no longer preserve the length.
Yeah.
Because the thing that's confusing me, because it's very obvious when you take the determinant both sides of that relationship there, you get the complex square of the determinant of u, which that equals 1. Which if you know you did, that breaks up the determinant of u being b to the I5. That's why I was asking.
Oh, cool. I'm impaired to do any kind of thinking right now. If you want to talk about this after, I will discuss that in detail. Okay. Yeah. So,
Yeah, sorry, I didn't quite get to what I meant to ask. In the example that you gave with Bob Analysis at the end, where he used a randomly chosen basis to decode the message, he got it incorrect a couple times. The example that you had on the board.
Yeah.
Because both of their the bases that they used respectively were public, and because they're unitary, once he has that information, is he able to like correct and work backwards to get all of the correct information, or is that information lost?
No, so after you measure, you break the state down into, so you break it from the superposition into one of the states. And we talked about one of these things, I forgot where it was. This? Yeah, the mutually unbiased thing. So after I project in the wrong space, I did this example on purpose. Like I tried to measure the zero state using the x basis, where I use the plus state, or I use this as the ket. So I lose all information, and all I just know is that I just get 1 or 0 randomly. So once I get this number, I can't work backwards, or I can't work on that qubit anymore, because now it's just a number. So yeah, things get collapsed, and we can't really treat things like superposition anymore. Well, I guess in practice you actually could, but everything gets weird and messed up, and nothing's going to work after you project, you're done. So you can evolve as much as you want, and the norms are preserved, and then as soon as you project, you can't go back and do anything. So that client in the example, if they were like to return the bill to the bank, like you probably didn't make new money because you've already had to observe the checking things actually. Anyways, any more comments or
One more. Can you go back to the slide that Allison brought?
Yes.
Of all the scheme you had there. There you go, perfect. Does that get general? I'm actually kind of curious. Does that get generalized for like higher qubits, like if you had like more qubits?
Oh, yeah, especially the example of 5 things here, but yeah, if you pick like, 100 things, you can just generate 2 binary strings of like 100 per alphabet, and you can.
All part, I meant to say like if you had each like character for the string, could that be, let's say 2 qubits each besides only being paired for one? I'm
There
curious
might be a
though,
way to do something.
have you seen that?
I have not, but I'm not sure, maybe that could be, like, but,
And what's that system, what's this system called?
uh.
Oh, it's just BB8.
BB84 crypto protocol. 1984, and then BB's reflecting it. But yeah, that's the classic final key distribution. Oh, you can actually, there's like, this is actually something you can buy for like probably millions and billions of dollars, but like, you can actually make these in governments, and people actually have these and you can communicate with them. But you gotta be like some some crazy rich company, and needs some crazy.
Right, yeah.
Crazy times to actually use it. So,
Quantum computing is very expensive.
yeah, anyways, but it actually is a thing you can do now. If you have much money.
Another, I know I'm asking a lot of questions, I'm sorry, it's a lot of questions. Another quick question is, how many bits, okay, I'm sorry. In order to do the secret key, I'm actually kind of curious. How many qubits would actually be? Because this doesn't look like it would be a very good secret key thing, because I can just based off of 5 qubits, I can easily predict, there's only so many combinations.
Oh, right. I mean, yeah, you in practice a lot more. It is only for distribution, so you won't use the shared key, and then you can use your other crypto algorithms to actually do your stuff once you guys have a shared key. But the purpose of this is just to, like, send a little message to make sure you have, like, you're talking to the right person or something. Anyways, yeah, sorry. Anyways, that's it. Thanks for coming, you guys.
Well, thanks for coming again. I hope you all have a good weekend and hope to see you next Friday.